All right, we're going to practice our compounded probability. This is page 4. We're going to find the probability of each scenario. Tossing a die and landing on 4. And means multiply. So possibility of, oh, I'm sorry guys, I circled the wrong and. Look at that. So there's and means multiply. So probability of a 4 times the probability of heads. So probability of 4 is 1 out of 6. Probability of heads is 1 out of 2. We multiply straight across the top, straight across the bottom. We get 1/12. Probability we flip 2 coins and both coins lands on tails. And probability of and, so multiply. So probability of tails, oh Peter, times the probability of tails. So we got 1 over 2 times 1 over 2. Because one coin does not affect the outcome of the other. Multiply straight across. We know we got a 1 in 4 chance. Pulling a blue marble or a green marble out of a bag with 3 green, 4 blue, and 5 red. Now, when I do these marble ones, if it does not say without replacement, we're going to assume we put the marble back. Whoops, sorry guys. Getting ahead of myself. So there's 12 total marbles. So probability of blue plus the probability of green, or means addition. Good job. So the probability of pulling a blue one is 4 out of 12. Green one, 3 out of 12. Probability of blue or green, 7 out of 12. King or club, addition, out of a deck of cards. Well, there's 4 kings and 13 clubs. But wait, there's a little bit of overlap because one of those clubs is also a king. So we're going probability of king, probability of club, minus our intersection of king and club. So 4 out of 52 plus 13 out of 52 minus 1 out of 52, because we don't want to double count that same king. 4 plus 13 minus 1 gives us 16. 16 divided by 52, and we math fracket. Tells me we've got a 4 out of 13 chance of that happening. Queen or even number. Or means add. There's 4 queens. There's 20 even numbers, if you remember back earlier. Do queens overlap with even numbers? No, they do not, so we don't have to worry about that. These are mutually exclusive of one another. So 4 out of 50, so probability that it is queen plus even, 4 out of 52 plus 20 out of 52, 24 out of 52, math frac is 6 out of 13. Flipping a coin and landing on tails, or rolling a 3 on a dice. Or means add. Great job. Okay, so flipping a coin, so probability of tails, plus probability of a 3. Does the coin affect the outcome of the 3? It does not, so they are mutually exclusive, so we don't have to subtract anybody. There's no overlap. So 1 out of 2 plus 1 out of 6. Could turn this guy into a proper fraction, or a common denominator, multiply top and bottom by 3. So we get 3 out over 6 plus 1 over 6. That gives me 4 over 6, which reduces to 2/3. Drawing a king, and without replacement, you draw another king. Okay, without replacement, that means I'm taking this card out, setting it off to the side, and then I'm reaching back in to see if I can't get me another one. So probability of king multiplied by the probability of king, given I already pulled a king. So remember, we're going to assume what happened happened. So the probability of king is 4 out of 52. The probability of a king given a king is 3, because we already pulled 1 out of 51, because we're reducing the number of cards in our deck. So 4 times 3 over 51 times 52. 12 over 2,652. Can't write in red. And we're going to hit math frac. Oh gosh, 12 divided by 2,652. Math frac. And we get 1 out of 221 chance. That's the chance that happens. You draw a club, and without replacement, you draw another club. So probability of club, and then probability of a club given club. So the first probability is 13 out of 52. We're not putting that club back in the deck. We're going to assume we pulled a club. So 13 out of 52, and then 12 clubs left, because I got a club sitting next to me. I just pulled it out. Over now 51 cards, because there's one less. 13 times 12 is 156. Well, we just figured out what that is. So 2652. Then we're going to hit math frac. 1 out of 17. Okay. And the last things on these pages determine whether or not we are independent. Remember, if we're independent of one another, when multiplied together, they will equal our intersection value. So the probability of C and D. So we're going 0.9 times 0.3, and that gives us 0.27. Does that match our intersection value? If it doesn't, which it doesn't here, our answer is no. And then the bottom one, 0.1 times 0.6. Well, look at that, 0.06. Do they match? Yes. So they are independent of one another. This concludes page 4.